Session of today. We have to kind of stick to the schedule because after that we have the formal dinner. So whatever, I have to be strict.
Okay.
And I first like to welcome Pierre, and she is from Paris, from Café Marie Curie. And she will talk about structured compressed sensing and some theoretical results.
Okay.
Welcome.
Thank you very much for the invitation. I'm very pleased to be here, and thank you to be still here tonight. So just to help you, because it's late, this talk is located between compressed sensing and Pierre talks, where there was many applicability in this one. Pierre got all the videos, so I got all the theorems. Okay, be prepared. And concerning Andersen's talk, the answer of question number 1 for this talk is no. Okay, so it can help you to locate my talk across all the talk that you've seen today. Okay, so let's talk about structured compressed sensing and also recent results about sampling in compressed sensing. So the first part is a motivation part, and it will be, I will a bit repeat what Pierre said this morning. Then I present the result of a general theory for compressed sensing and structured measurements, and I will finish with recent results on optimal sampling. So for the first part, this is a joint work with Jérémie, Bigot, and Pierre Weiss, okay, that we don't need to present anymore. And for the last one, it's a joint work with Ben Adcock. Okay, so you know now how an MRI works. So just quickly, we have this image, we observe the Fourier transform, or kind of. Let's say that we observe the Fourier transform, okay? And we are sampling along smooth trajectory, parameterized here by lambda. We have bounded speed, bounded acceleration, and typically you can take a spiral, which is fine. And the question is, of course, from the set E lambda, where this is just the Fourier coefficient that you observe across this spiral, are you able to reconstruct the image U? Okay. So this was the first question. There is a question on how to generate a curve lambda, but this is Pierre's talk. And the crucial question here is, what is the minimal amount that you need, or the minimal amount of time or measurements, depending your criterion, to get a given accuracy. Okay, and of course we want to reduce cost and to reduce to improve patient comfort. Okay, so I'm going to focus on MRI, but actually what I'm going to talk about can be applied to many other application fields. So you can take tomography, ultrasound imaging, or also interferometry, okay? But I stick to the MRI application, okay? So if you undersample and you still want to reconstruct exactly or in a robust way your image, you need to have a prior on your image, and this prior is that your image is simple, and in the case of image, we can say that it's sparse. So there exists a basis in which I can represent my brain image here, and I would have a few non-zero coefficient, okay? And actually, if I only keep 1% of the largest coefficient in magnitude of this decomposition, well, not this one, but the decomposition of this image in the specific basis, I can recover this, okay? So at least my signal is sparse in a certain basis, or it is compressible, okay? Okay, so of course you know that the sparsity for natural signals, natural images, can be obtained in a wavelet basis. So we set W to be a wavelet orthogonal transform, okay? And U is my image, my brain image that I'm interested in, and X are the wavelet coefficient of the image, okay? And X is sparse, U is not. So since it's X, which is simple, I'm going to retrieve X and not U, not the image, okay? So to do so, I will consider the basis pursuit algorithm, okay? Sorry, Anders. And so we minimize the L1 norm, which is promoting the sparsity of my wavelet decomposition of the image. And of course, I should satisfy some fidelity constraint. Okay. About theoretical results in compressed sensing, you have a combinatorial issues, and if you're not good at combinatorics, it's okay because you have a powerful tool which is random sensing matrices, and mainly theoretical results are obtained from random sensing matrices. So at some point I should stick to this setting, okay? But I will try to be a bit further than standard compressed sensing, okay? Okay, so again, just to be clear, we want to reconstruct this image, but actually we won't reconstruct this image. We will reconstruct the wavelet coefficient because this is a wavelet coefficient because almost everything is at 0 here, so this is sparse. I don't observe the image, but the Fourier transform of the image, and I don't observe the entire Fourier transform, just some points, so maybe a long radial sampling scheme or whatever you want, okay? Okay, so if I recast the problem of MRI in a compressed sensing way, I have here my Fourier matrix, my Fourier transform F, and I can model the acquisition process for MRI with the full sensing matrix A0, which is the Fourier transform times the inverse wavelet transform, because I want to reconstruct the wavelet coefficient. Okay. And then I should say, okay, when I sample one frequency in the K-space or in the frequency domain, if you prefer, this is just the scalar product between one row of this matrix and the signal that I'm interested in, so the wavelet coefficient, okay? And then I stack all my measurements and I can form the data vector Y, and Y is just AX, where A is my sensing matrix and is just an extracted matrix from A0, okay? Because I have subsampled my data. Okay. So if I look at what exists in the CS compressed sensing literature, the earlier result of Candestalo consider uniform drawings, okay? And the quantity of interest was the definition of this coherence, where n is the dimension of the signal times the maximum of the L infinity norm, of my measurement vector squared, okay? And so if you consider this coherence and you assume X is S sparse, so has only S non-zero coefficient, they show that the number of measurements that you need is of the order of this coherence times the degree of sparsity times logarithmic factor. Okay, so you can try to do uniform sampling in MRI, and you would not have anything in return, okay? Because here this coherence here is equal to n. This is an exclamation mark. Sorry, it's not a factorial. It's n just. But n is enough to say that it's doomed, because you ask the number of measurements to be bigger than n times s, so bigger than the dimension of the signal. Okay, so really bad. Okay, and then people work a bit, and they introduce the notion of local coherence, where now the quantity of interest is this, where you just sum the L infinity norm of measurement vector squared, okay? And if you assume so let's say you have your sampling matrix A, your subsample row in your full sensing matrix, and you will take the row AI, let's say, with probability pi, okay? And you just stack the measurement vector in your sampling matrix here. Then the number of measurements here is of the order of this coherence, kappa A0 times S. So this is okay. You will end with such a sampling scheme in the case of MRI, if you do so. But still, this quantity is still log n, so you're going to increase the number of measurements. It's not so good, and it's based on isolated measurements that Pierre said we cannot use in practice, okay? We need some smooth and continuous trajectories. Okay, and the last work was made by Ben Adcock, Anders Sensen, Clarice Boone, Bogdan Roman, and other, and also in the paper of Gita, where they assume a certain sparsity structure in the signal to reconstruct, and by doing so, they managed to kill here the log factor that we have for MRI, and they only ask for S log n measurements. Okay, but again, this work appeal to isolated measurements, and you cannot do it in an MRI. Okay. But when people are selling compress sensing, if you take the early paper of Lustig, Dono, and Polly, they say, okay, we have subsample, and compress sensing is telling us that that's okay, we can reconstruct using L1 minimization. But actually, this is not true, because we've seen that none of the sampling matrices considered before can really encompass this kind of structure in the acquisition. Okay, so this work, yes, but it's not because compress sensing theory justify it. Okay. So I'm not afraid to say that compress sensing theory are partially disconnected from application. Okay. Okay. But okay, so this is a typical compress sensing scheme. Okay, I have isolated measurements across some probability distribution, which is nice for MRI setting. This is the L1 reconstruction, and I have reconstructed a little sentence that I put inside my brain here. Okay, but actually, if I structure the acquisition, let's say I'm just doing horizontal lines in the Fourier domain. This is totally doable on an MRI scanner, because this is just continuous trajectory, and a very simple one actually. I can still reconstruct something. So I should be able to have a theory that explains this favorable behavior. Okay. Okay, so I will try to bridge the gap between what I observe in practice and what the compress sensing theory gave me. So let me do a first comment about the fact that I will only consider L1 minimization. In this talk, I'm of the school of you better choose your measurements instead of struggling in post-processing way. Okay, so I really want to emphasize on the choice of the measurements here, and so I only consider L1 minimization or basis pursuit, or when you have noise, quadratically constrained basis pursuit or less so, or whatever you want. Okay. So the idea to put the structure that I have in the acquisition, okay, is to introduce the notion of blocks of measurement. So I still have A0, my full sampling matrix, which models the physics of the acquisition, but now I'm going to define a block, and the block is just a rectangular submatrix of A0 that could stand for any pattern in the sampling space. So if I take A0, I partition the rows of A0, so the measurements vectors, into blocks that I call BK, okay? And then I will draw blocks, because I still need a bit of randomness for my theory. I will draw blocks B with probability pi, okay? So I choose the kth block with probability pi k, okay? And then I just stack the drawn blocks. And of course, I should satisfy this isotropic condition here. So if I just illustrate this rapidly, let's say that your block are a horizontal line or a segment in your acquisition space, then it means that you're going to take some block B1, which are a bunch of rows of A0, okay? And then you want to take the orange line or the orange segment, and then you stack the corresponding block, okay? And so on. And that's how you construct your sampling matrix here, A. Okay, and of course, as I said, this is totally covered by the previous framework that I just introduced. And it seems that it should work, okay? For this sampling, I should be able to reconstruct pretty well my image. So, at first sight, it could appear to be a bad idea. Why? Because consider A0 to be a D-dimensional separable transform. So, let's stick to D, okay? So, we want to reconstruct an image, a signal of size square root n by square root n, okay, of size n in total, but the image is square root n by square root n, okay, and I have A0, a separable transform here. And I suppose that in the acquisition space, so this is my signal, but for the acquisition, I just take horizontal line here, okay, as in my simulation. And so her horizontal line is of size square root of n, of course, okay? So I do so, and I can show that if I take m, where m is the number of horizontal lines that I take, which is less than 2s, where s is the degree of sparsity of this image, then there is no hope that I can reconstruct my signal, okay? So actually, this kind of structure has been solved previously by Lustig and Dono and Pauli. And I also said, yeah, we are going to do this in practice and it works, but I'm saying that here the number of horizontal line should be of the order at least 2s, which is a really bad news because it means that in total the number of measurements should be of 2s times square root of n, which is huge, okay? So this is a limitation proposition, but that says that, okay, if I want to structure the acquisition, this is totally incompatible with uniform exact reconstruction on the set of S sparse vector. So to break the limitation, I have to remove some part in this slide, and of course it will be the last one, which is that I don't want to reconstruct any S sparse vector, but I want to reconstruct a specific class of signals that have a certain sparsity structure, okay? Because in practice, the signals that I want to reconstruct are structured. Okay, so I need now a compressed sensing theory that can handle structure sparsity and structure acquisition, okay? Just to be more realistic. Okay, so let's do some definitions. So n is the dimension of the signal, m is the number of blocks of measurements that I take, not the number of measurements, but block of measurements, okay? When I write BS, it's just the restriction to matrix B to the column indexed by S, meaning that this is just the columns that are interacting with my signal, okay? Vs is a vector, and then when I say Vs, I just keep the coefficient of V in S. And Bk is my blocks dictionary. So I can define a new coherence that I call gamma S pi, which is the maximum between upsilon and theta is just here, okay? And upsilon is just here. So when I say, when I have, sorry, such a norm is just the sup of BVQ starting from P. Okay. Yeah, starting from P. Okay. So now my new coherence for my sampling acquisition modality will be gamma S pi, the maximum between those two quantities. So the main difference between the previous result that I just gave in the introduction is that here my coherence is depending on the whole support S and not only on the cardinality of the support, okay? And pi, the way I'm drawing the measurements. Okay, and then we have the following result. If I take a number of blocks of measurements bigger than gamma S pi and times logarithmic factor, then I will retrieve X with high probability, and I will have actually exact reconstruction. Okay, so the proof of this result is based on the golfing scheme approach introduced by David Gross and adapted to compressed sensing by Candace and Yannick Plan. Actually, we can also handle noisy measurements. Let's say that here we have a bounded L2 noise, okay? So now I'm considering the recovery problem of quadratically constrained basis portrait. And if I have the same amount of measurements as before, I have for free stability and robustness to noise. Okay. So the idea of this theorem is what? Is now, let's say that you have a modality acquisition, and we want to inject some prior on S to see how this quantity could be evaluated, because of course you don't know S, okay? But you can say, you can try to inject some information that you have on S in this quantity to see how it behaves. So this is the purpose of the rest of the talk. Okay, so we are going to evaluate this gamma, this new coherence, in several cases, okay? So first, I can do isolated measurements, which is the standard compressed sensing framework, because when I do isolated measurements, I just take row by row in my full sampling matrix, so my block is just a row. Okay? So I can do standard compressed sensing. If I do so, I have no prior on the support except that it's S-sparse, so I will retry the state-of-the-art result that the number of measurements should be of the order of S times the coherence, okay? Now let's turn to a silly case where you want to sample with the identity, okay? So you don't want to do so, because if you have something really sparse in the input of the identity, you're going to have something really sparse in the output of the identity, and then if you randomly subsample, you're going to miss the information, okay? And so you won't be able to retrieve anything with high probability. So it's really silly to do so. So if you consider the identity here, actually with standard compressed sensing, you will say that you need a number of measurements bigger than the dimension of the signal. So you cannot do compressed sensing. But now let's say that you have a prior on the support. Let's say that you know the support, which is a big prior, okay? So if you know the support, you can inject it in the previous theorem, and you will say, okay, I should sample only uniformly where my support is, and then I only need a number of measurements which is of the order of S, log S, okay? And this is actually related to the coupon collector problem, if you know it. Okay. Let's talk about ideal MRI case. So ideal, why? Because we do isolated measurements and we cannot in practice, but MRI, why? Because A0 is a Fourier times R transform, or Fourier times wavelet transform. And if you assume to have on the support the information that it's sparse by level, okay, sparse by subband, the subband of the wavelet, then you can show that the number of measurements should be of the number of the sum of the degree of sparsity by subband, Sj, and this is actually the state-of-the-art result for this case. Okay. Okay, so actually we here and here we match the state-of-the-art result, and here we are saying in this toy example that if you have coherent matrices, sensing matrices, it's okay, provided that you have enough information on the support. Okay. Okay, so now let's do structure acquisition. Okay, so I will stick to this setting where I am in a 2D setting, and I only acquire horizontal lines. Okay, so square root of n length horizontal line. So I do so, and now m in this slide is the number of lines that I take. Okay, the number of blocks of measurement that I take. If I do standard compressed sensing, if you recall the first proposition that was limiting in the beginning of the section, it was saying that so Fourier is separable, so I can apply my limiting proposition, and if the support is only S-sparse, I know that a necessary condition to have reconstruction should be m bigger than 2s. Okay, this was the bad news of the beginning of this section. Okay, this one. But now let's say that with the new theory you can inject some prior on the support, and let's say that you know that the support is concentrated on Q horizontal lines. Okay, then I can show that the number of horizontal line in the Fourier space that you need should be of the order of Q, the non-zero lines that you have in the space in the image domain. Okay. So let me illustrate this. Here you have a sparse signal, okay, but it's totally in structure. Okay, I have sparse coefficients, yes, but they are spread all over the image domain. I observe this signal in the Fourier domain using horizontal lines, okay, and this is the reconstruction. So I didn't reconstruct my signal, right? But now I'm saying, okay, I take another signal which has the same degree of sparsity as before, but now the sparsity structure along horizontal line here. Okay, there are just 3 horizontal lines that are non-zero. If I use the same sampling scheme, now I'm able to reconstruct exactly my signal. Okay, so it's pretty intuitive, right? Okay, and actually we can try to do the same experiment with the Fourier R transform. So Fourier was easy because Fourier is totally incoherent, so every computation is fine. But when you do Fourier R, the computation is more involved. And so the question is, if I'm doing horizontal line in the case of MRI like this, what should be the sparsity structure which is well adapted and which will be reconstructed by such a sampling scheme in the Fourier domain? Okay. So let me try to give you an insight of this. So people may think that this is just the number of non-zero coefficient by wavelet subband. So this is my, let's say, my wavelet decomposition. And as I presented you before, I can define the degree of sparsity by subband, okay, in each subband, to be the number of non-zero coefficient in each wavelet subband. Okay. But actually, this this quantity, the sparsity by subband, is the quantity of interest when you do isolated measurements, but it's not when you structure the acquisition. So it's not this, it's something more complicated. So remember, I'm always acquiring horizontal line in the Fourier domain, and now the structure sparsity that matters is the maximum number of non-zero coefficients that are aligned vertically across all horizontal levels. So if I look at all the first horizontal level here, what do I have here? I have 4 non-zero coefficients, which is the maximum number that I have across all these levels here. So S0C, for C for column, will be 4, okay? On the second level, I have also here 4 coefficients, so then S1C is 4, and so on, okay? So I can define the structure sparsity SLC to be the maximum number of non-zero coefficients aligned vertically across horizontal sublevels. So now I can say, okay, if I structure the acquisition in MRI like this, across horizontal line, then the number of horizontal lines should be of the order of the structure sparsity that I just introduced. This is the quantity that matters. It is not the total sparsity anymore. Okay. So again, just to illustrate this, let's say that here you have this kind of structure sparsity. Then you should choose a number of horizontal lines to be proportional to the number of black dots here in your Fourier domain. Okay. So let's do another experiment. So I take a bamboo image and I suppose that I observe this image through an MRI. Okay, this image will be sparse in the wavelet domain, and I can compute the structure sparsity that I just introduced for this image, and we will have this. Okay, and then I take this image and I rotate it from 90 degrees. So I didn't change the sparsity of the decomposition, okay? But actually I changed the structure sparsity that I just introduced, okay? You see that this one is much bigger than this one. And I use the same sampling scheme to reconstruct this one and this one, okay? So V small, H is big. So V good, H bad. And this is the reconstruction of V. and this is the reconstruction of H. Okay, so this was predicted by the previous theorem, saying this image is okay to be reconstructed with this one, and this image is not. Okay. Okay, so just to sum up, I introduced recovery guarantees with explicit dependency on the support and on the way you choose your measurement pi, your blocks measurements. We have a new class of sensing matrices, and we try to make the theory coincide with practice. But of course, I need a bit of randomness, okay, to use concentration tools. So now the tough questions that are left are: can we extend the theory when you have arbitrary physical constraints, not only block, okay? And if I give you a deterministic sampling pattern, can you say which kind of signal can I reconstruct? This is really the tough question remaining. Okay, there are also other applications, and yeah, I won't talk about that. Okay. So once we have this, we can say, okay, I could try to optimize the acquisition. Okay, I know that I have some constraints, so I have some to structure my acquisition, but I should optimize the acquisition, so the number of measurements should be smaller and smaller. So if I use the theorem that I just gave you, so if I use the coherence, which is just the maximum between theta and upsilon, and both quantity are quite ugly with respect to pi, it's quite difficult. It's non-convex. We have huge objects, and that's why we designed some numerical strategy to address this problem. And now you know everything about it. It was Pierre's talk. Okay. But I'm going to try to give you new result about theoretical optimal sampling. Okay, theoretical, I insist. Okay, so first, nothing is on the archive. This is an ongoing work, so please be indulgent. Be critical, because I will be glad to have any feedback, and don't steal the results because it's me. Okay. And now you know that I'm pretty good at argument. So recall, we have a number of blocks of measurement which is of the order of the maximum between theta and upsilon. Okay, this is theta, this is upsilon. If I want to minimize this with respect to pi, it's complicated. So my idea is to kill a quantity. If I have only one quantity, it's easy. Okay. So which one will I kill? I will just kill the ugliest one, as in movies. Okay. So let's kill upsilon. Okay. All the proof are based on concentration tools. And so if you play with concentration, either you're good at combinatorics, either you should add randomness. I'm not good at combinatorics, so I will add some randomness. Let's say that your signal x that you want to reconstruct is such that the sign of x restricted to the support forms a Rademacher or Steinhaus sequence. Okay, so it's just random signs. Okay, we have a random sign. If I measure my signal using y and using the sensing matrix structured by block, then I can show that the number of blocks of measurement should be only of the order of theta. Okay. With high probability, I will have then exact recovery and robust and stable recovery. Okay. So now I can try to minimize theta. Okay. So theta is just here. Well, this is the supremum of this quantity. Supremum almost surely, and you know that to optimize this, you should choose pi k, which will give you a constant here. So you should choose pi k to be proportional to this L infinity to L infinity norm. So here is the proposition. If we choose the drawing probability minimizing theta to be, so this one, with such a choice, we need the number of blocks of measurements to be of this size. Okay. So when we have structure measurements, it's quite difficult to see what happens. So let me just rewrite this result in a standard compressed sensing framework, okay? So I'm doing isolated measurements here. So if I choose the kth row with probability proportional to the L infinity norm of AK times the L1 norm of AK restricted to the support of the signal, then I should have a number of measurements of this order, okay? And I minimize the bound function of theta. So the take-home message here is when you do standard compressed sensing stuff, you should consider a way of drawing your sample to be proportional to this, okay? Let me just a tour of the literature on this question. In the seminal paper, we saw that we use uniform drawing. This is fine. This is fine when your transform is totally incoherent like the Fourier one, meaning that all the entries of your sampling matrix are of the order of 1 over n, okay? 1 over square root of n, if you don't take the square. Okay. Then people did variable density sampling, and they proposed to choose the drawing probability to be proportional to AK, the squared of the L infinity norm of AK. So what does it mean? It means that when you have an orthogonal transform, okay, so let's take A0 also orthogonal, okay, and A0 have rows A1 to AN. And the L2 norm of AI is always 1, okay, because I'm orthogonal. Okay, so if you ask this, if this is small, it means that the coefficient of AI are non-zero across all the entries of AI, okay? So when this is small, okay, I have here AI, and I have all the entries are non-zero, okay, and I can multiply here by a square, a sparse vector, sorry, and I will retrieve information of this sparse vector using this measurement vector, because I'm going to make a mean of all these components, okay, so it's okay. Now let's say that AK L infinity is high. So if it's high, since I have this condition of my measurements vector, I will have only a few coefficients that are non-zero, and I should have some which are non-zero, meaning that they are not really good to measure, except if I have information here, okay? So this theory say, okay, you can sample where it's coherent, meaning you should sample most the measurement vector that localize the information. And actually this is counterintuitive, because you should sample the measurement vector that localize the information if there is information at this support, okay? So this new result is saying, so it's okay, I should be incoherent, but of course I should have information if I am coherent in my measurements vector, okay? Okay, so keep this in mind. When you are doing isolated measurements or block measurements, the optimal drawing probability is depending on the local coherence here and on the sparsity structure of the signal S here. Okay. Yeah, so what happens for Fourier wavelet transform? So for Fourier wavelet transform, again, so A0 is my Fourier matrix or transform. I define the sublevel to be omega L, and I suppose my signal sparse by level, meaning that when I restrict the support to the sub omega L, I have at most little s L coefficient. Okay. I can try to estimate this theta in such a case for Fourier wavelet transform, and I have this following quantity, and then now I can say, okay, the probability minimizing the number of measurements should be of the order of what? Of the degree of sparsity restricted to the subband divided by the size of the subband, meaning that you just sample proportional to the proportion of information in your subband. Okay. So the question now is theta is okay. The question is theta sharp, or can I do better? So the idea is to introduce a new quantity, lambda, and so you can play the two differences game between theta and lambda. And what's the difference? Here I put an S, okay, and here I don't have it. So I don't have interference between the support and of the support. Here I just stay in the support, and I consider the 2 to 2 norm, okay? This is just the spectral norm. Okay, then using the the proof that I use for theta, I can slightly modify it, and I can show that if my support is, if my signal is still random, random signs, then the number of measurements m should be of the order of this lambda s union st, where st is lying in of the support, okay, in the complementary of the support, times logarithmic factor. So why do I like this theorem? Because this theorem is kind of oracle type result. Why? Because here, when you look at this, you have the 2-2 norm of almost the support, okay? And if you knew the support, you could invert AS, and what matters in this case is just the condition number of AS. So lambda, in a sense, is almost controlling here the condition number restricting to the support, okay? So that's a theorem that comforts me. And actually, the idea is, okay, if you don't care about logarithmic factor, you can just enlarge the support of one element, okay, and you will have an upper bound for this for this quantity, and you can say, okay, if I choose the number of measurements to be bigger than this lambda S tilde, where S tilde is a fat support of one element, then I will have recovery. So now let's try to do to finish numerical experiments. So I stick to the 1D, okay, 1D case. I'm in dimension 2048. I have the Fourier wavelet transform A0. Okay, I consider 3/7 plus the resume part. I have a sparsity by level structure, which is like this, okay, so across the 4 levels. And I have a total sparsity to be of 3%. Okay, so I will generate, I will generate 100 signal with this structure, okay, and then I will try to reconstruct them. I use here the standard compressed sensing probability distribution, which is maximizing the old coherence, okay. I will use the probability which is proportional to the new term that I just introduced, and then you can see the difference now. I'm really localizing to the center of my Fourier space, and I can also compare actually to the lambda criterion that I just introduced about the optimality of theta, where lambda was just the 2-2 norm, okay, so you can see the difference. Okay, so I perform 15% of measurement with each probability profile. I do 100 realization of signal, and I try to recover them with 3 different ways of drawing measurements. And this is a box plot of the results. So this is standard compressed sensing reconstruction. This is the one depending on theta. This is the one depending on lambda. Okay. So I hope that now you're convinced that local coherence is fine, but structure sparsity is also very important, okay, for reconstruction and to be taken into account on your way of sampling. Okay, so I don't have any position opportunity, but this is the view from my office, and yeah, but I should add that we have 6 Fields medalists and 90 Nobel Prize in this university. And actually, if you're a secretary or an administration staff, you can go to the 33rd floor of the Damancy Tower in the UPMC, and this is the view. So Paris Descartes, you can you can be quiet.
Everyone can go to our balcony.
I can. I have a key. I have a key. Okay, so I'm ready for your question. Thank you.
Thanks a lot for this wonderful talk, and I think we have time for 2 or 3 questions. Okay, please.
On one slide, you had a problem that you skipped multiple coils, parallel imaging.
Yeah.
In parallel imaging, you are faced with sensitivity profiles of the different coils. Would this lead to using or to choosing different lines for acquisition in different coils?
So actually, this is the work of Ben Adcock that tried to use this block of measurements for parallel acquisition. And for the moment, so you can try to include the sensitivity profile, but it's a hard problem. And for the moment, the answers are not really satisfactory because you need a number of measurements that scale linearly with the number of coils, so that you don't want, of course, because you want to combine all the coils together. So yeah, works need to be done still in this area, but I didn't formalize it with my approach. Yeah.
Okay, another question? If that's not the case, then we're exactly to the time schedule, and I thank you.